Batteries are the silent architects of our modern world. No longer confined to the remote controls or flashlights of the past, they have become the fundamental backbone of global progress. From the smartphones in our pockets to the satellites orbiting the Earth, these energy systems quietly power the critical infrastructure of our daily lives. As we transition toward a sustainable future, the scale of battery integration is truly staggering. They stabilize our electrical grids, keep massive data centers online, and provide the lifeblood for a new generation of transportation. Understanding this technology is essential as it sits at the very heart of how we live, work, and communicate. At its core, a battery is a sophisticated conversion engine. It doesn't just hold electricity like water in a tank. It stores potential in a chemical form. When we demand power, a controlled reaction occurs within the cell, transforming that stored chemical energy into a steady, reliable flow of electrons to drive our devices. Peering inside a battery reveals a masterclass in precision engineering. While it may look like a simple container, it is a complex assembly of specialized layers. Every cell relies on a delicate balance between the negative anode, the positive cathode, and the vital components that manage the flow of energy between them. The anode serves as the primary reservoir for energy during the charging phase. Typically constructed from layers of graphite, it acts like a high-capacity warehouse. It securely holds onto lithium ions until the moment power is needed, at which point it releases them to begin their journey through the system. Opposite the anode sits the cathode, the battery's positive terminal. This component is usually composed of specialized metal oxides and determines much of the battery's overall performance. It acts as the destination for ions during discharge, and its chemical makeup dictates how much energy the battery can hold and how long it lasts. Connecting these two sides is the electrolyte, a specialized medium that facilitates internal movement. While it is a conductor for ions, it acts as a barrier for electrons. This selective permeability is what allows the battery to function, creating a controlled environment where chemical signals can translate into usable electrical current. The separator is a thin but critical gatekeeper. Its primary job is to prevent the anode and cathode from touching, which would cause a short circuit. However, it is engineered with microscopic pores that allow lithium ions to pass through freely, maintaining the essential balance required for safe and efficient energy transfer. When a battery discharges, a fascinating migration occurs. Lithium ions move internally from the anode to the cathode. Simultaneously, electrons are forced to take the long way around through an external circuit. This external flow is exactly what we harvest to power everything from small electronics to industrial-scale machinery. Charging reverses this entire process. By applying an external voltage, we push the lithium ions back across the electrolyte to the anode, effectively resetting the system. This cycle of migration is a masterpiece of electrochemistry, allowing us to reuse the same energy storage system thousands of times over its lifespan. Individual cells are rarely used alone in high-power applications. Instead, they are combined into modules to increase capacity and voltage. This modular approach allows engineers to scale the technology, creating energy systems that are perfectly sized for anything from a residential home backup to a massive utility-scale storage facility. The assembly process continues as these modules are integrated into large-scale battery packs. This structural engineering ensures that thousands of individual cells work in perfect harmony. By grouping cells this way, we can achieve the massive energy density required to move heavy vehicles or support entire neighborhoods during peak demand. Modern energy storage systems are becoming the primary partners for renewable sources like wind and solar. Because the sun doesn't always shine and the wind doesn't always blow, these high-capacity packs bridge the gap, ensuring that clean, green energy is available 24 hours a day, exactly when it is needed most. Managing this much energy requires a sophisticated digital brain, known as the battery management system. This computer monitors every individual cell in real time. It ensures that the load is balanced, monitors for any fluctuations in voltage, and makes split-second decisions to keep the entire system operating within its optimal performance window. Temperature is the greatest enemy of battery efficiency. As energy flows, internal resistance naturally generates heat. To counter this, advanced packs utilize integrated cooling channels. These systems circulate specialized fluids to whisk away excess thermal energy, ensuring the cells stay at a stable temperature, which is vital for both safety and performance. If heat is left unmanaged, it can lead to a significant drop in efficiency and even damage the battery's internal structure. This thermal energy comes from the friction of moving electrons and the chemical reactions occurring within the cell. Engineering effective cooling is just as important as the chemistry of the battery itself. Like all physical systems, batteries eventually age. Over hundreds of cycles, the internal materials begin to degrade slightly, and the movement of ions becomes less efficient. High temperatures and frequent deep discharges can accelerate this process, gradually reducing the total amount of energy the battery can hold over time. We measure the health and capability of a battery through 4 key metrics: voltage, capacity, current, and power. Voltage represents the electrical pressure, while capacity tells us the total energy stored. Current and power define how quickly that energy can be delivered, dictating whether a battery is suited for long-term endurance or high-speed performance. Safety is the absolute priority in battery design. Modern packs are equipped with multiple layers of protection, from physical pressure vents and fuses to electronic fail-safes managed by the software. These systems work in concert to detect anomalies instantly and isolate any issues before they can affect the rest of the pack. When we build these systems, the focus is on reliability and longevity. Every component is tested under extreme conditions to ensure it can withstand the rigors of daily use. This commitment to robust engineering is what allows us to trust batteries with our most critical infrastructure and our transition to a cleaner future. The manufacturing of these cells takes place in highly controlled environments called Gigafactories. The level of precision required is incredible, with automated systems handling materials at the microscopic level. This scale of production is what has allowed battery technology to become more accessible and affordable for the entire world. In the automotive sector, battery integration is revolutionizing how we move. By placing the battery pack low in the chassis, engineers improve vehicle handling while providing silent, emission-free power. These integrated platforms are the foundation of a transportation shift that is faster, cleaner, and more efficient than ever before. A completed battery pack is a marvel of integrated engineering. It combines the cells, the cooling systems, the structural shielding, and the power electronics into a single, cohesive unit. This holistic design ensures that the system is not only powerful, but also resilient enough to last for a decade or more of service. As the first generation of large-scale batteries reaches the end of its life, recycling becomes paramount. We can now recover up to 95% of the valuable minerals like lithium, cobalt, and nickel. This prevents waste and significantly reduces the environmental impact of mining, creating a sustainable supply chain for the future. By closing the loop through recycling and remanufacturing, we turn the battery life cycle into a continuous circle. This is more than just energy storage. It is a foundational technology that empowers a sustainable civilization. Thank you for joining us as we explore the hidden engineering that powers our world.